having me over. This is my first time here, and whatever I've seen till now, it has been very impressive. I have known Alan for almost close to 10 years now, because we have been graduate school together, but Entanglement has been for 10 years. So I'm going to give three lectures on entanglement, entropy, and holography, and I was told to keep this basic, keeping graduate students in mind, so I apologize from the beginning if something is too basic. The plan of my lectures is that the first 2 hours, that's today, I will talk about some basic concepts in quantum information, in quantum mechanics, about entanglement. And it's very big words, I'll shorten it to EFT, and then I'll talk about basic concepts in EDS-CFT, because I was told that I should assume knowledge of first year, one course in general relativity. And so this is, hopefully, and I will reach this part. I will talk about the Ryu-Takayanagi entanglement entropy formula in the context of holography, and I'll show you some applications. So this is the idea for today. I don't know how far I'll reach, but hopefully I'll reach up to this stage. So this is the content of one. And tomorrow I'll talk about some recent progress. So I don't know, depending on the interest that is there in the audience, I might actually talk about the derivations of this formula. Or I could talk about something called relative entropy. So let me, so to the graduate students who want to learn more about this topic, there are lots of online resources. Just do a search for holographic entanglement entropy and you get lots of matches. I think this is a very active area of research, and it has been so for the last several years. So let me begin by making some non-rigorous motivational remarks, and hopefully I'll make some of these rigorous as time progresses. What is the idea of entanglement entropy? The idea is that you have a region in space-time, and suppose you wanted to understand what information can be gained from a small region of that entire space-time. Then, and suppose, to put it a little bit more in context, suppose you were an observer and you did not have enough resources to measure what is very far away, and you were just restricted to this local region, then you would be tracing out the degrees of freedom that are living outside this region. So that's what you would be doing, and then there will be some entropy that is associated because of the loss of information, and that is the rough notion of entanglement entropy. This is very similar to the picture that you have in general relativity, where you have a black hole, and at least classically, whatever is inside the black hole cannot come out. So this was one of the original reasons why people were interested in pursuing this entanglement entropy, black hole entropy correspondence. And so, as you may know, that black hole entropy is related to the area of the horizon divided by 4 times G Newton. That is in Einstein gravity. You might think that even entanglement entropy might be related to, and this is a question mark, to some kind of area. So this was one of the original questions that people started investigating in the early 1980s, and they indeed found a lot of similarity, except that, just to give part of the story away, that indeed it was proportional to the area, the leading term was proportional to the area, but instead of 4 times G Newton, what you got is something that was infinite. So you had some ultraviolet cutoff raised to some suitable power, instead of the Newton constant here, you got infinity. And this had to do with the fact that there were ultraviolet divergences in field theory. So okay, so that's observation 1. Another observation or another motivational remark is that entanglement entropy is a very useful non-local order parameter. And one example is that if you have a 2 plus 1 dimensional gapped system, then the entanglement entropy in this system goes like so. In all cases or most cases, there's a leading term that is proportional to the area. So here it is the perimeter of some entangling surface, perimeter divided by some cutoff. But there are also interesting subleading pieces, and the interesting subleading piece in this particular case happens to be a constant, and this is called the topological entanglement entropy. And this piece is a useful useful measure of topological order. And the final example that I'll give, or final example that I'll give why one should be interested in studying entanglement entropy is that suppose you wanted to quantify the number of degrees of freedom in field theory. Well, in this particular the example that I have in mind, I'm talking about the special class of field theories which have conformal symmetry. Then this entanglement entropy can be used to quantify the number of degrees of freedom. So in particular, for even dimensional, so even D field theories, there are subleading corrections, as I said, that there are subleading corrections to this leading order result. In even dimensions, at some point you're going to start getting log terms, so log of the size of the entangling region divided by the ultraviolet cutoff. And it is this coefficient that is sitting in front of this log term that provides us with a measure of the number of degrees of freedom. So this is the coefficient sitting in front of the log term in even dimensions. And this is also related to what are called trace anomalies. And this is useful for a completely different reason, and the reason is that instead of talking about entanglement entropy, you could have just focused on the trace anomalies, but in odd dimensions there are no trace anomalies, but you still have a universal piece. So this is in even dimensions, and in odd dimensions the subleading term actually starts off with a constant. There is no log term, but there is a constant. And that constant can be used to provide a measure for the number of degrees of freedom. So just to make things a little clearer, what do I mean by that? So what I have in mind is a number of degrees of freedom that can be thought of in the Wilsonian context, that when you are going from the UV to the IR, you are integrating out degrees of freedom. So you might expect that the degrees of freedom would decrease, and this quantity, this either the constant or the C actually provides us with such a measure.
Sorry, excuse me. So for odd dimensions, if it's just a constant, wouldn't it be regulated to an extreme dependent then?
Not for conformal field theories. Not for conformal field theories because we can talk about this later. But for conformal field theories, it's not scheme dependent. Yeah. Okay. So far as this intuition is concerned, that when you integrate out, it should have some kind of a monotonic behavior. So CUV should be bigger than CIR. This is a very active, or this is a very active area of research, because you can prove theorems here, and these are called C-theorems. Starting off with the famous homologic of C-theorem in 1 plus 1 dimensions. So this has a bit of history. 1 plus 1, and this was proved in 1986. This is in 1 plus 1, and there was a conjecture by Cardy that in even dimensions, for example in 3 plus 1 dimensions, there was a conjecture that was only proved as recent as 2011 and goes by the name of the Kolmogorov-Kishimer proof for the A theorem. In odd dimensions, so this is all in even dimensions. So this is in even. In odd dimensions, the status is the following. So in 2 plus 1 dimensions, Myers and myself, we made a conjecture in 2010 that this universal piece would satisfy this monotonic property, and this was actually proved by Cassini and Greta in 2012. And I should actually point out that there's some caveats to this proof, but then I'm happy to discuss this in private. But there's a proof of this using entanglement entropy. So in fact, the proof for this homologic of C-theorem in 1 plus 1 dimensions can be made using entanglement entropy as well, although I don't have time to do that.
Field theory proof or holography?
No, field theory. The statements that this is the field theory proof using entanglement entropy. All these statements are all field theoretic proofs.
Like in some particular areas, right? Circles.
For certain. Yes.
Then you can map to thermal.
Yes. That's right. Yeah. So I don't want to make that more precise because I'll run out of time if I wanted to go there. Okay, so that's a few reasons why one should be interested in understanding this entanglement entropy more in detail. The another comment that I should make that will set this lecture up in context is the connection of entanglement entropy with geometry, and that is made clear through the ADA-CTP correspondence. So the rough picture that you have is that according to the ADA-CTP correspondence, you have some field theory that is living on the boundary of some space-time, and there is an extra radial direction for z. So this entire space-time is what gives you ADS space. This is ADS space, this is the boundary, this is where the field theory lives. And you're interested in understanding the amount of quantum information in some region of that space-time on the boundary. And as I'll try and explain, the answer is going to be given by some minimal, the minimal area surface of some region that extends into the bulk. So this is the bulk, this is the boundary. And so you could turn this question around and ask how much of this bulk geometry is actually needed to describe a certain region of the space-time where the conformal field theory lives, and that's where the correspondence with geometry comes about. Okay, so these are all, as I said, I'm going to begin off with some semi-rigorous remarks, and hopefully, as the lecture progresses, some of them are going to become.
How do I know, or what do I expect from the gravity side? This picture with the black hole where the entropy is thermal entropy or entanglement entropy. From the field theory side, sort of clear what one thing is and the other thing is, but here we sort of
it depends on, as you know, I think you know that, depends on the size of the entangling region. The minimal surface either wraps around the black hole, if just the leading term becomes the black hole entropy.
No, I know, but say you want to make a cartoon like this, it's not obvious from gravity.
Absolutely.
What kind of entropy this should be?
Sure.
Would you say this question is settled?
No.
Oh.
So far as the entanglement entropy, so suppose you wanted to consider the entanglement entropy between the Hawking pairs that are one is falling in, one is falling out. And originally people thought that maybe the entanglement entropy of that is the reason why black hole entropy arises. But of course they realized that there was an infinity. So right now the understanding, depending on how you want to look at it. So if you are talking about an induced gravity, so this is just for you. So if you are talking about an induced gravity, then that epsilon, the hash that I've written there is finite and can be thought of as a Newton's constant. But otherwise, the entanglement entropy actually gives you a correction to the actual entropy. So it's not really. So that's the understanding of this black hole entropy and entanglement entropy correspondence.
The problem is that from field theory, one would say one is a quantum effect while the other one is a thermal effect. But in gravity, they mix because the temperature is a quantum thing. It's not always how to tell each. How to disentangle them.
Yeah. Okay. So let's start off with some basics. I'll start off with by pretending that I'm a quantum information person for the next. I'm going to talk about, right? I'm going to define a few things, and the idea is I'm going to talk about. So be on the lookout for the following. That I'm going to talk about something called strong subadditivity. Strong subadditivity. And I'm going to define this quantity, and I'm going to tell you how to prove it in ADCFT. The quantum mechanical proof is very lengthy and very complicated. So that's one. The other thing that I'm going to talk about is something called relative entropy. And this relative entropy satisfies an inequality. It's supposed to be positive. And I'll show you, probably tomorrow I'm going to show you some explicit checks why it is positive in holography. So just be on the lookout for these two terminologies. So let me start off by defining the von Neumann entropy. So von Neumann entropy is a quantum mechanical version or quantum mechanical notion of what is called the Shannon entropy in classical information theory. So if you have, given a quantum state psi, we can construct a density operator rho. So this is density operator rho hat, frequently called hat, is constructed in the usual way. And then the von Neumann entropy for this density operator, this is my notation, is given by trace rho hat log rho hat. This log is actually with base 2, so this is log with log 2. I'll drop this 2 log, and in fact there's an ambiguity with respect to the base, but then for convention says that it is with base 2. So what do I mean by trace rho hat log rho hat? So if the eigenvalues of this density operator rho hat are lambda x's, then this is minus summation over all the eigenvalues lambda x log lambda x. Okay. So let's do an example. This is a canonical example, and a very nice example. One reason it's good to do these examples because I think, and you should correct me, so when we learned quantum mechanics as graduate students, we did not really learn it this way. Yeah, so many of the terminologies were, even as far back as 10 years, were not really taught in a conventional graduate course. So let me do an example. So an example, let's consider a particular state, which is called the Bell state. It is also called the EPR state. So psi is, and you can think about, I'll explain what this means. So this notation means that this is in a product Hilbert space. So this is A direct product with B. So one means that the polarization is pointing up. You can think about it as a photon polarization is pointing in one direction, and 0 would mean it's pointing in the other direction. one with polarization up, the other one with polarization down, and so on. So one here represents that the photon has polarization in one direction and 0 in the other direction. So that's what this notation means. This is also what is called a qubit. So from here we can define what is called a reduced density matrix. Density matrix is defined as, so rho subscript A means that I'm taking the full density matrix and I'm tracing over B. That's what it means. That's a reduced density matrix. So there are two systems, A and B. And so from here, I can construct what is called the bipartite entanglement. Bipartite means it has got two systems, bipartite entanglement. S, the function of rho A, is minus trace rho A log rho A. Then you can easily check, it's a straightforward exercise that you construct the density matrix. So rho for this example is psi with psi. This works out to be a half 1 0 0 1 plus 0 1 So from here, so the first entry corresponds to A, the second entry corresponds to B. So if I trace over B, that means I'm just sandwiching this operator between the eigenstates for the B Hilbert space, and I get this rho A to be simply 1. So this corresponds to a matrix, a 2 by 2 matrix. So, and then, so eigenvalues are half, so S of rho A is simply log 2. And in fact, you can do the other way around as well. You can compute rho B, and you find that it is again log 2. It's a straightforward exercise. And this is an example of what is called maximally entangled state. So any state which has got, so if the dimensionality of the Hilbert space H is D, then the maximally entangled state will have entropy log 2. Okay,
So
now
the convention of the bar is you put A in the first position.
yes, A in the first position and B in the second position. Yes.
I mean, for both bra and cat.
Yes. So I do not flip it. Yeah, that's right. So even for this is A. Okay. So let's consider another example, and this is going to be quite. So this was what is called a Bell state. It's an example of an entangled state. Now I'm going to give you an example of what is not an entangled state, and we'll compute the entanglement for that and see what happens. So this is not an entangled state. The way that you see that this is not an entangled state is because you see that this can be written as a direct product. Like this, and any state that can be written as a direct product of a state that belongs to the Hilbert space A times another state that belongs to the Hilbert space B is not an entangled state. But of course, if I give you a complicated state, many entries, it's not very easy to check whether it's entangled or not. So let's compute the reduced density matrix again in the usual way for this particular case. Again, you can check that rho A in this particular case will have half with got eigenvalues lambda, 0 and 1, and the entanglement entropy in this particular case is, the definition was lambda log lambda plus. So there are two eigenvalues, so 0 log 0 plus 1 log 1, so 0 log 0 is 0, and 1 log 1 is also 0, so in this particular case it's 0. So if you have a state, so this implies that if you have a state that is not entangled, it's reduced, the entanglement entropy for one system and the other to 0. Okay? Okay.
Inverse is also true?
I'm sorry?
The inverse is also true?
Yes. Yes. So, yeah. So if you have if you have something that is not 0, that means that it corresponds to a state which is not entangled. I'm sorry, it's entangled. Yes.
Sorry, what is lambda?
I'm sorry?
What is lambda?
Lambda is eigenvalue for this density matrix, and the definition was lambda times log lambda. Yeah, I had a nice analogy so far as the classical definition of this Shannon entropy is concerned. So classically, Shannon entropy is also defined in the same way. The lambdas are probabilities. So the Shannon entropy measures the classical uncertainties in some probability associated with some probability distribution. And why should it be log of something? So the analogy that I had in mind was the following: that imagine a lecturer is giving a lecture, and there is only one student in the room, and there is a probability p that the idea that the lecturer is supposed to communicate goes through. So when it goes through, the lecturer can test it. Obviously, he'll test it by asking questions. He depends on his mentality. He'll be surprised that the student has got the concept. So let's assume that he's surprised if the student has got the concept. And now consider there are many students in the room, and depending on the number of students, you assign a probability pi that he's being able to communicate that idea to that student. Maybe that probability depends on the fact that the student is listening, or maybe it's working on the iPad or laptop or whatever. And so what is the amount, or how do you quantify the amount of surprise that the lecturer has if the idea has got through? So obviously, if it goes through, say 2 students or 3 students, it's additive. Whereas the total probability that it has gone through everybody is multiplicative. If you want to quantify this amount of surprise that the lecturer feels, you have to define a measure that is additive. And log is such a measure, because log of something, the total probability is going to add up. Okay, so log of P1 times P2 is going to be log of P1 plus log of P2. So, and yeah, of course.
Why do you have to multiply by rho in front of log?
I'm sorry?
Why do you have to multiply by rho again in front of log?
Oh, that's the average. So from the classical side, it's the average uncertainty. It's a measure of the average uncertainty. And then you sum over all the p's. Yeah. Yeah, it's the average surprise in my context. Yes. Okay. So let's make a note of this formula, because this will turn out to be useful when I go to. So this is not particularly useful, particularly when you try and talk about this quantity in quantum mechanics, because you really don't know how to calculate log of some density matrix. So rather than use this, there is another way of doing that. That forms the basis of what is called the replica trick.